Do we have any questions about the problem statement?
Very
Any
similar.
thoughts?
It's very similar to the first task we solved today. So basically, we just need to have a sliding window that goes to all the points, and size of sliding window is determined by whether difference between two x values is less
Yeah,
or
it's
equals
less
to
than
k.
yeah, okay. Yeah.
And inside of that sliding window, we need to find two biggest y's, right?
Two biggest y's. Okay.
Yeah.
I was planning on just calculating this formula and every time that the window gets too big, we find out whatever is the biggest valid window we have, and just compute this formula and do a max on that, because it's a longest window kind of a problem, right? So we have to wait till the window gets violated.
Okay, so
yeah, we do need to compute this formula. It's just inside of the formula, we need to put some values into y's, right?
Yeah, okay. So this is the formula, right? Yi plus yj plus xi minus xj here, right? So we know that, j is going to be greater than I. So, x's are sorted, right? So we know that xi is going to be less than xj for sure, right? So we know that this is going to be equal to yi plus yj plus xj minus xi. Okay, so we can definitely have a sliding window, and we will keep expanding as long as xj and xj minus xi is less than or equal to k. But what are we trying to maximize here? We want to maximize this guy, right?
Yeah. Well, when I said two biggest y's, yeah, now it doesn't work.
Yeah, because you can have two y's that are big, but maybe their x's are very close, right? So on a high level, what does this mean, right? So this is the difference in x, right? This is the sum in y. So you have two things at play, right? So you want to find 2 points that have in the current window. In the current window, you want to find 2 points that have very big y's, right? But on the other hand, just because they have big y's, it doesn't mean that this is going to be the best answer, because they also have to be they also cannot be close, right? Because you also want to maximize this xj minus xi. So, well, another way of looking at this, let's rewrite this. This can be rewritten into xj plus yj plus yi minus xi. Okay, so j is the right bound, right? J is, for a given sliding window, let's say that this is, okay, let's say that this is going to be our window, right? And this is j, right? So I is somewhere in this window, right? In this window, it may not be here, right? So I is, I can be here, right? We want to find the I that maximizes this result, right? So, well, but for a given j, this xj plus yj is fixed, right? We just want to find an I that maximizes the difference, yi minus xi. Okay, so in the previous problem, we were finding that we wanted to find the maximum value in a given sliding window, right? It's just, and also in the previous problem, it's not two-dimensional, right? Here, it's every point is two-dimensional. You have both x and y. In the previous problem, it's one-dimensional. You can think of it as just, you just have a list of x's, right? So in the previous problem, okay, you are given, the sliding window only contains a bunch of x's, and you want to find the maximum x, right? Now we have a bunch of tuples of x and y's, right? And you want to find the maximum yi minus xi. So it's really the same idea, right? You can still use a Q, right? It's just, the purpose of the Q is no longer to find the maximum x. The purpose now is to find the maximum yi minus xi, right? So what is the rule for the Q then? I mean, in the previous case, we pop a Q, we push to a Q. Before we push something to the Q, we compare that with the end of the Q, right? And we want to keep a monotonically decreasing Q if we want to find the maximum value, right? So it's really the same thing, right? So, okay, so in this example, the first item is 1, 3, second item is 2, 0, next one is 5, 10, and 6 minus 10, right? These are our points, right? So if we want to find, remember, our goal is to maximize yi minus xi, right? So initially our queue will contain 1, 3 because that's the only thing, right? Okay, then we see this 2, 0, right? So are we just going to push 2, 0 into our queue? Well, we compare again, we want to have a monotonically decreasing queue, but what's the rule for the decreasing? What does it mean for a point to be smaller than another point? This is our rule, right? Yi minus xi. So 2, 2, so for 2, 0, 0 minus 2 is minus 2, right? And this one, 3 minus 1 is 2, right? So if we want to have a monotonically decreasing queue, then 2, 0 should be here. 2, 0 should be here, and we should not pop. We should not basically, of course, 2, 0 should be here, but we should not pop this guy. We should not pop 1, 3 because 3 minus 1 is bigger than 0 minus 2, right? So basically, you can say that 1, 3 is a bigger element than 2, 0, right? Here, bigger means that yi minus xi is bigger. Okay. So now next, we have 5, 10. Then so 5, 10, 10 minus 5 is 5, right? So basically, you can say that 5, 10 is bigger than any of the previous 2 points, right? So we will just pop them out of the queue, and we will just push 5, 10 into our queue, right? So 5, 10 is the current max, right? Then 6 minus 10. Basically it's 10 minus 6, right? That's minus 16. So that's much smaller. So we will have it here, right? So in the current queue, the maximum is 5, 10, right? So this is almost the same as the previous problem. It's just that now the rule is slightly different, right? We want to find what are we maximizing? We're no longer maximizing x, or y, we're maximizing y minus x. Okay. Any questions? No questions. So does anyone want to implement this one for us? I mean, if there's no question, then I assume that anyone can implement this, right? If you feel like you cannot implement this, then you must have some questions.
From the queue, maybe I forgot the context. I understand how you build the queue, right? How do I get the answer? Can you go back to the problem statement, maybe?
Sure, I can copy the.
So okay.
Okay, sorry, this is a way to. Okay,
how do I get to the answer here, right? I see the queue contains 5, 1 and 6, 10 now.
Okay. Yeah. So your question is how do we get to the answer? Okay, so this is our input. Okay, again, our formula, the rewritten formula is okay,
y minus x, right?
xj, yeah, y. Okay. Yeah. Okay, so this is the formula. Okay. So, well, if our subarray only contains 1, 3, then our goal is to find the maximum value, right? We want to maximize this thing, right? So of course, our subarray needs to contain at least 2 elements, right? Okay, so initially our subarray just contains 1, 3 and 2, 0, right? Mm-hmm. So what is the answer here for this subarray? Basically, yeah. So it's
1.
It's 4, right? Okay, so it's 4. Okay, so what does that mean? So that means that the best you can do, so this is very important. So the best result when j is equal to 1 is 4. Okay, now let's expand the window. Now j is here, right? So this is your j, right? So okay, so now our sliding window contains 3 elements, right? So first of all, is this a valid sliding window? Now, so we need to check this guy. We need to compare their axes, right? So this is not valid, right? Because 5 minus 1 is bigger than 1. K is 1 here, right? So this is not valid. Okay, so we need to shrink it. Okay, so our current window contains this, right? But then 5 minus 2 is still bigger than k, so we need to shrink again. So okay, so it only contains 5 now. So basically, yeah, the best result when j is equal to 2 is nothing, right? Is no. There's no way you can form any sliding window ending at 5, 10, right? Mm-hmm. Yeah. Okay, so we will increment. We're going to move our j point to here, right? And yeah, this is our current sliding window, 5, 6, right? So 6 minus 5 is less than or equal to 1, so we're good, right? So this is a good sliding window. Now, what is the best you can do when j is equal to 3? Well, so in this case, our sliding window only contains, our window is of size 2, right? But this is a very, this is probably not a good example, right? In some general sense, your good sliding window can be very long, right? And this is your J, right? So anything from this point, because everything after this point, the X is going to be greater than or equal to this. Let's call this like X0, right? And this is Xj, right? So anything Xi between 0 and J is going to be greater than X0, right? So anything in this window is valid, right? Now the question is, so how do we pick, which I do we pick in this sliding window? How do we maximize this, Xj plus Yj plus Yi minus Xi, right? So, so this is the same, this is, let me repeat the analysis, right? So Xj plus Yj is fixed, right? Because J is the current J, right? So Xj and plus Yj, there's no flexibility there, right? But the flexibility is in the I. Which I do we pick? We want to pick the I that maximizes Yi minus Xi, right? So how do we find the maximal Y minus X? Well, we use the Q technique. Does that answer your question, Anu?
So I get the so on the head of the Q, you would have the maximum Yi minus Xi, right?
Right. So
what about the second element?
What about the second? What is the second element? You mean the second element in the Q, or why do we care about the second element in the Q?
No, or maybe I'm missing here. I need to get the answer 4, right? How do we get that? I have only one element.
Well, so Yi minus Xi you can get from the head of the Q.
Yeah.
Right. Also, you're asking about Xj plus Yj.
Well,
J is J is the right pointer, right? So here, if J is here, then Xj plus Yj is what? Is minus 4, right?
Oh, okay. So every time you calculate.
Yeah.
Okay, got it. Okay, sorry. Yeah, maybe I'm missing that.
Sanish, do you want to try it?
Okay, yeah, let me try. So first of all, we have since we have points, we will need the points is each one of them has 2, right? So X and Y. Okay, so technically there's still that will calculate. So it's Y minus. Okay, we'll anyway need so to track the window, we'll need that maximal, the Q or the linked list. We'll need something of that kind. So we'll need the linked list. I might have to look up this API actually, linked list of and so what we are adding, we have to add full value actually. So we have to, as we go, we have to compute this thing. So but we are maximizing only on Yi minus Xi, and we're looking for the max of the Yi minus Xi. So if we set the Yi minus Xi of this, so first of all, we should have that same while loop where we are rejecting everything else. So while everything less has to be taken out. So is first total. Okay, so this will be more complicated because this first dot value, this is already pre-computed as no, but then I can't do that because when I'll take it out, if I just store the integer values, then when I'm taking them out, then how will I know if I just knew what the maximum value was? What is we are not points that satisfy.
So one way is you can store like tuples, right? You can store the index and also Y minus X. So this is going to be easier for you to compare.
Yeah, this cannot be a simple int. So, well, if we've stored the whole thing, then just storing the point will also be enough.
So this int array is going to be like the tuple, right?
Yeah, two.
Okay, yeah.
So, and then over here we'll have ll dot first dot value, and then we can do Y minus Xi, value of 1 minus. Okay, I don't think it works like this. So we have to keep moving J till that K thing is met. So points. Block bracket. The first one is the X, the second one is the Y. So 0. So this is the we have and A has to be incremented. Or so the last value is the max, which has to go into the. So we must have had a max, which is over here, the equation. So that max is equal to max of with mx of whatever is the last value that we could get out of the linked list. And that last value that we had in the linked list, we know the point, and but this is nothing to do with one point. This has to be done with the I and the j. So last what did the last value remembered? How do I remember one point? That is the question. So what did we add over here? Wait, add first is wrong. So when we added the, what am I adding? Adding dot is empty. This DQ. I'm sorry, but I'm really confused with this link. Because this idea of using the DQ as a linked list is just still new to me. So when I was at each of the entries in that DQ or linked list essentially is a point, or is the way that I've done this. It is a point, and I'm not sure that was right, because the algorithm was that essentially we for each point we have the concept of a bigger or a smaller point, as you explained. So when the bigger point comes around, which means yi minus xi, then it's displacing the smaller points, and hence every entry is a point. So yeah, there's nothing wrong with that. So j, this is fine. So this is points. We added the first point. So when we are taking out, so maths equal to the max is the last value. It's and which is a point in his yi minus xi. Values 1 minus. You have to add the other two also. So yj plus xj. So, but this should be under an if, because while the points we are only shrinking the window, and there should be an if over here. I think I've completely confused myself now, so I'm not making progress.
Okay. Then I mean that's okay. I can just share my code.
Yeah, I'm sorry about that.
That's fine. But please, after the class, please.
Yeah, I think I need to.
Yeah, use linked list to implement all of the problems we have discussed today.
Yes, I think I have this linked list part has really gotten me even more confused. Sorry about that.
Yeah. Okay, so this is my code. I mean, pretty standard, right? So, this is the queue, right? So what are we appending into the queue? We are adding the index and the thing that we're comparing with, right? Yj minus, here I'm using j, so y minus x basically. So yeah, so this is the code that we update, we push to the queue, right? We make sure that the queue is monotonically decreasing, right? And well, this is basically, we're checking if the window is valid, right? So while x minus so this is just the condition to make sure that yeah, xi minus xj is less than or equal to k, right? So yeah, if it's not valid, then we keep shrinking. Then we update the result, and then we add the current value to the queue. That's it. Very simple, right?
Can you explain line number 7?
Well, I mean, this is xj is the is the x. I mean, this is just the same as this line, right? Xj minus xi less than or equal to k.
Is the xj is the one in the head of the queue, or
no? J is bigger than I, right? I is less than j here.
So I understood that line number 13, 15, we are adding the one, and then we are y minus j, yj minus xj, right? So that is the one with the maximum value, right?
Yeah.
So the xj is the one in the head of the queue?
No, j is at the end of the queue. J is at the end of the queue, right? So that's why we are, we're just adding xj plus yj, right? But I is the one that we are trying to maximize, right? So, and what is I? This is the 0th index of the queue, right? This is the head of the queue. And 1 here means, because I'm storing a tuple, right? So 1 is really the basically x, so the difference in y and x.
Okay.
Right. So here, this is saying, okay, we need to shrink it, right? If the difference between xi and xj are too big, get greater than k, then we need to shrink it. Now, what does it mean for us to shrink the window? That means that we need to pop from the, if this, so that means that we need to pop the queue. Any other questions? So, so all of the problems today that we're dealing with are related to sliding window, but really the technique has nothing to do with the sliding window, right? The technique is a monotonic queue. And this shouldn't be like entirely strange to you, because if you're familiar with stacks, then we have done something very similar to stacks as well. We have monotonic stacks, right? Usually monotonic stacks are used to find like the closest value to the the closest value that's like larger than you to the right of you, and also the closest value that's closest in terms of location, right? So the closest value to the left of you that's greater than you or something. We of course we will later on we will do a class about probably two or three classes about stacks, where we will talk about this monotonic stack, right? But I mean, today's monotonic queue uses the same idea, right? If the point is, if we want to find a maximum in the sliding window, then if initially you have an 8, then to the right of 8 you have something bigger than 8, then we know for sure that this 8 will never be used. Well, this 8 will never be the answer, right? Because you have something to the right of 8 that's bigger than 8. So that that number is more likely to be the maximum value than 8. 8 will never be the maximum number in the sliding window, right? Yeah, if it's never going to be the answer, then we can just pop it, right? That's how we can achieve that's how we can find the maximum value or the minimum value in of one time, right? So I recommend that, well, not only do you have to be familiar with the concept, more importantly, you have to be able to code it up. So so really familiarity with the API is super important. I think it's actually worse if you have the idea. So I mean, the best case scenario is, of course, you have the idea and you quickly implement it, right? But if you have two candidates, one is struggling with the idea, but if once they sort of after some hints they get the idea, they quickly code it up, then that performance is actually better than someone else who has the idea but cannot quickly code it up, right? Because in the end, we're hiring people who can code, right? Where like the ideas are good, but most likely in work you will not be coming up with monotonic queue solutions for any for anything. But you of course you have to write code every day, right? So really familiarity with the API, being able to quickly implement anything is more important. And if the interviewer decides that okay, this candidate's coding skill is weak, or their familiarity with their best language is weak, okay, then actually that's usually a quick reject. All right, but on the other hand, if your coding is very good, it's just that you require some hint to get to this monotonic queue idea or something, then that's actually not an immediate reject. Sometimes this is still hireable, right? Because as I said, ideas are like techniques, those like algorithm techniques are less used at work than real codes.